Can everyone see the screen all right, and can everyone hear me?
Yeah.
Perfect. I'll make a start. There'll be a few people wandering in and out. That's absolutely fine throughout the session. That's the nature of these things. So, and we're all very close together in terms of the parallel session. So I'll just start. So we've got lunch at 12:45. So I'm going to make sure we're wrapped up in well before then, in good time. So that will just be outside in the atrium as well. So what I'm going to talk about is some of the extreme weather events that we've seen in across middle latitudes of the northern hemisphere. So, in other words, areas such as the UK, but spanning across much of Eurasia into Russia and also parts of North America, Japan, parts of China, for example. But I'm going to focus particularly with some of the last 10 or 15 years extreme weather events that we've seen in the UK, but how that is linked with global warming. So, just as a bit of background, we've experienced in the UK this year the highest temperature ever in Cambridge, in the instrumental record in the UK. In Cambridge a few weeks ago, 38.7 degrees at the Botanic Gardens in Cambridge at near the end of July. So that was the warmest UK temperature on record. And we've also had the highest winter UK temperature on record in the instrumental record this year as well. So that was 21.2 at Heathrow at the end of February, 26th of February, I think the date was. So this year we've seen new extremes in temperature in the UK, which is obviously reflecting the overall warming trend. But there are some more subtle changes in extreme weather. It's not all just about high temperatures and heat waves. There's also some other extreme weather events that are being affected over the UK and other middle latitudes of the Earth's surface in the Northern Hemisphere by what we're doing to the climate. So I'm going to talk about some of these events and some of the possible causes, ways that global warming is causing these events in the next 20 or 25 minutes or so. And I'll have some time at the end of this to take some questions as well. So I'm sure you've all seen versions of this graph here. This is showing temperature changes over the last 170 years or so. So the graph starts just after 1850, goes through to last year. This is the very latest global temperature. And the reason there's different coloured lines on this graph is that we have different estimates or different groups that are estimating from weather stations around the world. And then they do some kind of modelling or statistical reconstructions because you're not measuring temperature everywhere around the world. There's several thousand weather stations and there's ships that measure temperature, buoys in the ocean and so on, and more recently satellite data. But there are parts of the world's surface where you don't directly measure temperature. But nevertheless, we have a pretty good record going back to about 1850 or so. There were lots of ships navigating large parts of the world's oceans back to that date, for example, as well as a considerable number of land-based weather stations. What you can see from this graph, and again you will have seen, probably many of you, versions of this, is an acceleration in global warming since, in the last few decades. So I was born in 1973, for example, so that would be about, I should have marked it on the line, but since about that time or just afterwards, you can see actually most of that global warming, or about half of it, is in the last few decades, and it's an accelerating rate of change. And in fact, in the last decade, we've had several of the warmest years in that instrument-based temperature record. So I do a lot of work on ice sheets, particularly Greenland, and all an ice sheet is a giant glacier based on the land. So there's 3 of these ice sheets. There's 2 in Antarctica, 1 in Greenland. So this is from my first trip to Greenland. I took it in a picture in 2001. This is actually the front of the Greenland Ice Sheet, where it doesn't actually reach the coast in most parts of Greenland, but it occupies about 4/5 of the island. So this is in an inland ending area of the Greenland Ice Sheet. You can see some icy boulders broken off, but these are about 20 or 30 metre high ice cliffs, and you can see the equal to scale here. So, and this edge of the Greenland Ice Sheet has been retreating very rapidly over the last few decades, so by several kilometres, for example, as the ice sheet is melting and losing mass. So if you melt the whole of the ice, then that will take admittedly a couple of thousand years, but there's 7 metres of global sea level rise. But the point is that you actually melt lose mass significantly a lot sooner than the time taken to remove the whole ice sheet. So within the next 50 to 100 years, the estimates at the moment suggest several tens of centimetres of the global sea level rise projections that you've just seen in Beth's talk, for example, will come from Greenland. So Greenland is a significant contributor to global sea level rise. Of course, there's other contributors. The Antarctic ice sheet is also losing mass. There's 2 ice sheets down there. They're actually bigger than Greenland. And then you've also got expansion of seawater as it gets warmer, called thermal expansion, that also causes the sea level to rise as well. Now, hand in hand with climate change, as I mentioned at the beginning, is an increase in extreme weather events. So if you look at the green and the blue bars here, these are basically weather-related disasters as catalogued by one of the big global reinsurance companies called Munich Re. So this is actually quite a recent update of their data. There's a particular way they define these, but I don't think it matters too much in terms of showing the trends how you define these. It's a very significant increase in terms of these meteorological events, so things like tropical storms, extratropical storms, local storms, so a mix of hurricanes, cyclones, tornadoes, windstorms, which affect UK, for example, but across the world, and then hydrological events, so floods, droughts, and then geological things like landslips that are linked in with failure of hill slopes because of extreme rains, that sort of thing. So those are the blues there. The reds haven't really changed very much, so these are the earthquakes, tsunamis, volcanic activity. There's a steady background. They change a bit from year to year. You can see there's no overall trend. So obviously people do die from these disasters. They are significant, but you're not getting the same kind of increases for the climate-related events. And of course the yellows are actually climate-related as well. So everything except the red sort of graph is increasing. So this is from basically Munich Re data. Something like a 4-fold increase in the last 4 decades or so in these meteorological climate-related disasters. As I mentioned, new records are being broken. Not every record is linked with greenhouse gas increases, of course, but the fact that we've had more severe records or extreme records being broken, and a number of these records, we do statistical analysis to analyse in relation with climate change. So this is the recent temperature record from Cambridge, which was a new all-time UK temperature record. And in fact, the actual global, this is very similar to a map that Mark Macklin showed in his talk yesterday, is showing warm temperatures. These are higher than our average temperatures for the month of June this year, June 2019, are in yellows, oranges and reds. You can see much of the globe is enveloped in these colours, particularly Europe. Do you remember European heat wave, 45.6 in South France, some places down there in June. And again, the heat wave was repeated a few weeks later in July, but also up over Greenland. So you can see that's got oranges and reds as well. There's been a high level of melting of the Greenland Ice Sheet this summer. In fact, I just did a radio interview on one of the US stations just a couple of days ago about that. But that's been a big interest to scientists and been in the news a lot in the last few weeks. So many places in the world have been unusually warm this summer, which reflects the graph that I showed a bit earlier of the global temperatures going up. Of course, there is variability. Some months, not every month is equally as warm as this, but the general trend is relentlessly upwards. July, again, you can see the oranges and reds. The patterns shift slightly, but the UK, that's when we had the extreme temperature in Cambridge, of course, but June it was also quite warm, I think. And again, Greenland's still quite warm. So this is reflecting general global warming, but global warming is not the same everywhere in any given month. So the patterns shift around, and this is related to something I'm going to briefly talk about called the jet stream, which most of you will have come across or been affected by, possibly if you've taken flights or whatever. But obviously in terms of storms that impact on the UK and parts of Northern Europe in the winter, the jet stream is really important in driving these weather systems. So the jet streams are giant currents of airflow that flow in middle latitudes of each hemisphere. But because in this part of the world we're particularly subject to changes in the jet stream, that's very important for controlling extreme weather events. Now actually in the UK, this summer has been quite variable, I would say. June was quite wet in this part of England, but actually we also had some record heat as well recently in Lincoln. And then last summer we actually had a drought. This is my weather station at home in Newark, which is about 20 kilometres from here. And you can see the grass is all burnt brown, so that was reflecting a month-long drought last summer. And then severe fires in parts of Europe, particularly last summer. UK had a record large fire somewhere near Manchester, Saddleworth Moor, but also Greece and Portugal particularly badly affected last summer in 2018. And these are what you would expect. With an increase in temperature, it gets warmer, drier, with shifts in the jet stream, gets weaker. I'll talk about that in a moment. And so, of course, some of these secondary effects of disasters become more frequent or the effects more severe. However, what we've also seen in the last 15 years or so in both seasons, in summer and in winter, but we're looking here at summer, is some extreme wet episodes as well. So this is looking 12 years ago in summer, for the month of June 2007, which some of you may well remember who are local based. We had some record rainfall over much of England and Wales and parts of Scotland and Northern Ireland, but particularly, in actually this part of the country and a bit further north and west, so Sheffield and Hull were particularly badly affected. In fact, there were a few people actually killed and severe damage to infrastructure because of flooding. So that was actually a record wet month for June for quite a few decades. Not unprecedented, but it was the wettest for quite a while. And that was one of the effects in Sheffield. In one of the, I don't know if anyone here knows Sheffield, but I was working in university there and lived there for a while. So that's one of the main streets near the centre of Sheffield, and people had to be airlifted from the roofs of office buildings in that particular part of the city as a result of the River Don bursting its banks from that extreme rainfall episode in June 2007. Just 5 years later, in 2012, there's almost a repeat performance. Now this map, these show, basically the blue colours are where you've got more rainfall than normal, so it's up to, like the last map, this is now for summer 2012, the whole of summer, so that's June, July and August. We've got more than 170% in large parts of this map, where you've got deep blues of normal rainfall for an average summer over the last 30 years. So it was actually a record wet summer in at least for 100 years or so in averaged across England and Wales. The instrumental records only really go back reliably for rainfall for about 100 years or so. And actually we've seen this summer was very wet in parts of England in June again, and of course we had the floods in Wainfleet in Lincoln. So there's just this swap of central England again encompassing parts of Lincolnshire was actually unusually wet this June, and it's linked to the jet stream, which I'll talk about more in a moment. But this is a bird's eye view on the North Pole. The UK is near the top of the map. Can you see the blue purple block near the top of the map? You see the UK outline there, and that is actually showing, that blue block near the top of the map, this map is showing where you've got lower air pressure, and low pressure disturbed weather, so more rain. Whereas over Greenland, you've got yellows and reds, high pressure. So there's kind of a seesaw. So when the air pressure is low over the UK, it tends to be high over Greenland because of the movements of the jet stream, or the other way around. So basically, our weather is connected with weather changes over the Arctic, over Greenland, which in turn has been affected by global warming. So I mentioned that this year we recorded the warmest UK temperature on record so far. But also we've had some severe cold snowy episodes in winter in the last 10 years or so as well. So this is actually almost exactly a year before that record warm day that I've just shown you in the previous slide. So if we just backtrack, this was 26th of February this year, 70 Fahrenheit, 21.2 degrees Celsius in Kew Gardens in London. If you go back almost exactly a year before, 1st of March 2018, this was very widely in large parts of certainly England and Wales, the coldest coldest March day in over 100 years. I know it's the start of March, so it's almost slightly cheating a bit, but this is actually showing, I think, the Millennium Bridge in London, So you can see the direct impacts there. But also we've had other recent winters where we've had some of these severe cold snaps that actually haven't been seen for a few decades, at least at that level of severity. So for example, in 2009, this is Sheffield, for example, and again, actually Sheffield was actually gridlocked for a day or two in December 2010 because of very deep snows, the deepest snows in Sheffield for almost 100 years, I think. So what's going on? So yes, the climate's getting warmer, but we're also seeing more extremes. In fact, this graph is for winter, and it's basically showing oscillations in the jet stream from year to year, from the last 120 years through to the present. So that's the year 18, almost 1900 through to last year. For the month of December, can you see that the ups and downs in the graph, going from left to right, are actually doubling in terms of the actual amplitude of them, or the amount that's going up and down. And this is basically indicating variations in the jet stream, the strength of it, across the North Atlantic for the month of December. We don't fully understand the reason why, but this is something that I found from research, working with a group of people at the Met Office and University of East Anglia, Sheffield I was at the time, a few years ago, and I almost accidentally just stumbled across this data showing this pattern of increasing variation in the jet stream. But this does explain why in winter we've actually had more extreme weather events in the UK in the last decade. So we've had some record cold, snowy winter spells, but we've also had some flooding and record warm winters as well, such as is shown on the top photo on the right of the slide here. So what's going on? The clue I would suggest is what we're doing to the climate is the main reason, and particularly with the what we call the Arctic amplified global warming. So if you look on the top of the map, can you see there's a big red swath going all the way across from left to right there? That is basically, the whole map is showing different levels, how much the world has got warmer, or how much warmer than for an average period it's been in the last decade. For the last decade. So global warming is strongest over the high northern latitudes. And the reason for this is various what we call feedbacks in the climate system, that basically it involves melting of ice and snow, removal of sea ice from the deep parts of the ocean, removal of land ice. As that ice melts, the meltwater is darker than the ice, so that absorbs more radiation from the sun, which heats up the surface. So this is one feedback that accelerates the warming regionally of those high northern latitudes of the Arctic regions. There's other effects as well in those high northern latitudes that accelerate the melting ice. But in turn, as it gets warmer, it melts more ice and snow. So it's kind of a runaway process. And to a certain extent, it's also happening down in the Antarctic. You can see around the peninsula here. So global warming is not equal everywhere. Regionally, there are differences. It's particularly strong in the Arctic. However, for those of you who come from the tropical Pacific or subtropical Pacific regions, quite a few of you in this room, as you know, as all of us know, it's always warmer near the tropics than at the poles. But as the world's getting warmer, as we warm the polar regions more than the regions nearer the tropics, what does that do to that difference of temperature between the equator and the poles? Reduces it, yes. Yeah. So that temperature gradient, normally it's always warmer to some extent nearer the equator than the poles. As you warm the poles more than the tropics, you're reducing that temperature difference. That temperature difference is actually like a heat engine that drives the jet stream, which is a strong belt of west to east flowing winds that flow around the middle latitudes of each hemisphere. So as you're removing some of the power of driving that jet stream, at times, the jet stream always varies, but at times you're on average weakening that jet stream, and then that has an effect on extreme weather events over regions like the UK. So this is a kind of a theory at the moment, and the reality is a bit more complicated in the sense that there's lots of factors that drive the jet stream, but it is one of the main ideas that I'm currently working on together with, in fact I'm just having a workshop on this again in a couple of weeks' time with an international group of other scientists as well. But actually this is, I shouldn't have done this, I know, and I throw my hands up as more guilty than many people, but this is from a climate meeting in Alaska, photographing sea ice near the North Pole. over the Beaufort Sea north of Alaska, where a part of the world where you normally expect quite a lot of ice even in the summer, and you can see there's big gaps in the ice. So that's anecdotal, because I'm not obviously this is just a surreptitious picture, so it's not like I've gone to the Arctic Oceans to do field work and photograph the sea ice each year. But if you look at the sea ice data, I'll show you in a moment, you can see there's a massive decline, and again, many of you will have seen this in news reports, and the amount of frozen seawater near the Arctic or in the Arctic Ocean over the last few decades. So, and this ice becomes weaker and more likely to be broken up each summer. You can see here there's cracks and fissures in the ice, and this is just, someone gave up the plane seat so I could just take pictures for 2 minutes, just a couple of lucky snaps just a few weeks ago, so I thought I'd just show them to you from sea ice recently near, well, about 80 degrees north latitude north of Alaska. And this graph here, particularly the red line is showing sea ice, changes in the amount of sea ice coverage over the Arctic Ocean for the month of September. The reason we're looking at September with the red line is because that's the month each year when the Arctic sea ice in its seasonal cycle shrinks to its lowest extent or lowest cover. The black line is for March. The winter ice is a bit more resilient, but you can see in both seasons, in winter and summer, it's going down by something like 50% for the red line. The numbers on the scale here are showing percent differences in the cover of sea ice for the whole Arctic. So the ice is shrinking, the ice cover, but it's also doing this as well as shrinking. It's getting thinner as well. So if you then look at the volume of the ice, it's actually reduced by something like 75% since the late 1970s. So in the last 40 years, we've lost 3/4 of the sea ice in the summer season in the Arctic, and that's a tipping element, or a tipping point, if you like, of climate change, because as you're removing that sea ice or shrinking it and thinning it, you're actually releasing heat, particularly in the autumn, from the ocean, which stays relatively warmer than the air each season as the air is cooling down in autumn. The ocean is relatively warmer, but as you're removing the sea ice, your sea ice is a very good insulator. You're effectively radiating heat into the atmosphere. So this is another mechanism for accelerating global warming in the Arctic, is this removal of the sea ice cover through this extra heat being released from the ocean in areas that were previously covered with sea ice. So the theory that I've mentioned to you a few slides ago, the idea that as the Arctic is warming more strongly, and the Antarctic to a certain extent, than the areas nearer the tropics, you're weakening or reducing the temperature difference between the equator and the poles, which in turn weakens the winds that drive the jet streams. The upper level zonal winds decrease. Those are the jet stream winds in each hemisphere, in the middle latitudes of each hemisphere. And in turn, that actually makes the jet stream wavier as it gets weaker, although that's a bit more contentious, the idea between the jet stream getting weaker and wavier, so that's an area of active research, that's why the box is dashed here. But there is certainly a potential, and I think we see evidence for this from the observations from the last 15 years or so, that as the jet stream slows down, it gets wavier, then you can get more what we call stuck weather patterns, or weather patterns sticking around for longer periods of time nearer the Earth's surface, in middle latitudes of the Northern Hemisphere in particular. And this may well be one of the main driving influences of some of these extreme weather events in the UK. And we've also seen similar increases in other middle latitudes of the Northern Hemisphere. Just to mention one example, extreme heat and forest fires in Russia in 2010, for example. There were also floods in Pakistan, I think, in the same year. And of course, California has had extreme heat and droughts and fires as well in recent years. So these areas are also in middle latitudes or low middle latitudes that are being similarly affected by changes in the jet stream, just at different points around the world. So more persistent weather patterns, extremes more likely, probably because of what we're doing to the climate system. So it's not just a case of the average temperatures going up, so we're getting more heat waves, but it's also, there's more floods and droughts sticking around for longer at various points on the Earth's surface because of this weakening in the jet stream, or at times more cold snowy events, which is a bit counterintuitive, isn't it? You wouldn't necessarily expect more cold snow events as a result of global warming. But if the jet stream gets weaker over the UK in winter, then the tendency is to actually at times draw in easterly winds from Siberia. So that's what we've seen some of the weather events that I mentioned, the one last year at the beginning of March in 2018. So the jet stream gets weaker and wavier, partly as a result of global warming. Another effect is actually, for example, pushing Hurricane Sandy into New York, I think in 2011, wasn't it? So hurricanes normally take a track where they curve out from the Caribbean into the North Atlantic and they decay. But if the jet stream changes shape and becomes more south-north waving, or vice versa here, then it can actually influence the tracks of storm systems and hurricanes as well. So there are some scientific studies published by some colleagues of mine who actually looked at the influence of Hurricane Sandy, the track having been changed by the altered jet stream pattern. So there's another possible effect of this strong warming in the Arctic. And in fact, from some of my own work with colleagues in the US, you can see from this is actually a map for summer for the last 12 years or so, so average of June, July and August data for looking at, this is really wind patterns or air pressure patterns in the Northern Hemisphere. The UK is at the top of these maps, the North Pole is in the centre of each map. Can you see that on the left map, which is for summers for the last 12 years since 2007, particularly in the top half of the map, the jet stream is marked by the boundary between the light blue and the dark blue colours. Can you see it's wavier than on the right map? The right map is for a previous 30-year period, which is 1971 to 2000. So the right-hand map is a more uniform jet stream flow, where the jet stream is marked by the boundary between the light blue and the dark blue. If you look at the left map, which is the last 12 summers, then you can see a more wavy configuration of the jet stream. So 12 years isn't very much. There is natural variability, but with the very strong warming in the Arctic, there is there is certainly the possibility that this is affecting the jet stream at times further south. So it's not. I mean, we never prove anything fully in science, and we don't have many years of observations. But there are many groups working on these issues now in terms of how different spatial patterns of global warming can affect jet stream patterns. And there seems to be increasing evidence over the last 3 or 4 years that this is certainly having some effect at times on the jet stream, and therefore extreme weather. So what happens in the Arctic? There's not many people living there. It doesn't stay in the Arctic, but can affect latitudes further south where hundreds of millions of people live in terms of extreme weather events. As I mentioned, my own work concerns Greenland. So this red blob over Greenland, high air pressure in summer, blue blob near the UK and Ireland is low pressure. So again, this is average for the last 12 summers. So June, July, August 2007 to 2018. The difference from a previous 30-year period, so that we have more low pressure, which is unstable weather near the UK, which on average, not always, but on average gives us wetter weather conditions, more disturbed, more jet stream disturbances, if you like. Whereas over Greenland, the air pressure's got higher, and actually this red line here on the graph is Greenland's air pressure over the Greenland area, averaged over the last century and a half or so, through to the present date. Can you see a record high values of the red line in the last 10 years, 20 years or so, compared with the previous time period? What we think is happening is that as Greenland has got warmer in the last few decades, it's actually increasing the mass of air over Greenland. As air gets warmer, it expands. So you're getting a giant dome of air forming over Greenland, which is actually pushing the jet stream further south over the North Atlantic. Normally it had been north of the UK, but in these last 12 summers it's been more often over England and Wales. So that probably explains, at least in part, why we've had some of these very wet episodes in summer in the last 10 or 15 years. And of course we've seen these extreme melting of the Greenland Ice Sheets 7 years ago. This is in 2012, when all this area coloured in pink and red temporarily melted off the surface of the ice sheet for a few days in July 2012. That was the first time that had ever been observed from modern data. It has happened before, but not since 1889, and before then for several centuries.
And then it's actually almost happened again this summer when more than 60% of the ice surface melted at once. So we've got a tendency towards, as Greenland and the Arctic gets warmer, there's more ice melting. In fact, just after this event in 2012, this is me standing, I was doing field work with a Danish team on one of the nearby glaciers. This is actually the Greenland Ice Sheet in the background here, lots of icebergs in the fjord. Can you see the glacier surface I'm standing on is very dark because it's wetted by all the ice melts, and as you can see, with increased melting of the ice, you're absorbing more energy from the sun, which accelerates that warming of the surface, and in turn you get more further melting of the ice cover, and of course that's sea level rise. So currently from Greenland we're losing something like 250 billion tonnes of massive ice each year. So it's unstable, it's already contributing significantly to global sea level rise. Satellites can weigh the ice sheet directly, they've been doing this since 2002, and we've actually had a more than doubling of the amount of mass lost each year from the Greenland Ice Sheet, if you look at the trend of the satellite data since 2002. This is meltwater running off from the Greenland Ice Sheet, from a glacier right next to the Greenland Ice Sheet that I did field work on. And that tunnel in the ice that you can see here is a giant hole in the ice that collapsed within a year after that I took this photo, because that glacier is rapidly retreating. And then very briefly I'll show you a YouTube video clip of the one of the very spectacular results of that melting of the Greenland Ice Sheet in 2012, where a bridge almost got washed away. Well, it did actually get washed away. So I'll just show you this very short video clip. This is near Kangerlussuaq in southwest Greenland, where I showed you the picture of the ice sheet front near the beginning of the talk. That's the main road bridge in the town. It's the main international airport in Greenland is there actually. And that bridge has been there since the 1950s. It wasn't designed for that amount of meltwater coming off the edge of the ice sheet. And they're trying to shore up the bridge. It was an exercise that ultimately failed because no one was killed or anything, but the bridge got quite broken after this was taken. So a bit too much for the distance, I think, isn't it? Ultra light is quite an appropriate video. So I've actually stood at on that bridge, not then, but 11 years previously, and that's just an amazing level of water flow compared with a normal summer 11 years before that. So it gives an idea of the level of change of melting and loss of mass of the Greenland Ice Sheet. So last couple of slides. So this summer we had I'm still analysing the data with a team of scientists across the world, but we're looking at some of the data of melting from this summer and some of the climate data, so that's quite an exciting but worrying as well, obviously, project that I'm involved with. And we're going to see, obviously, further increases because Greenland's warming very rapidly. This is from a field trip to Greenland, and we sailed directly past this enormous iceberg in a tiny boat. But this was grounded. You can see where the water line has pushed the iceberg up. And this is a broken off bit of the Greenland ice sheet. And of course these happen all the time, but again we've had an increase in these in recent years. And again I've looked at some data that actually show something like a doubling of the amount of icebergs breaking off of Greenland in the last few decades. So these events, basically everything's connected. So a bit like in the previous talks you've heard, everything's connected between regions because jet streams connect different parts of the
hemisphere. So with strong warming over the Arctic, more loss of sea ice, loss of glacial ice over Greenland, but more often poor weather over the UK, for example. But also there's extreme weather in other parts of the northern hemisphere, middle latitudes as well, that I've not really had time to go into in very much detail. Finally, what about the future? This is an artist's rendition of London in 2100. The IPCC, so this is the conventional story that you've just heard from Professor Elizabeth Holland, that is likely to be too conservative, but nevertheless is still quite worrying from this baseline from the last Intergovernmental Panel on Climate Change report. You can see what they're saying about the Arctic for the rest of this century compared with the last 30 years or so. On the top right map here, where you've got purples in the top of the map in the Arctic region, where it's warming a lot more rapidly than the rest of the world, something like 10 degrees warmer than recent times. So imagine the amount of extra sea level rise that comes from that amount of warming in the Arctic and the Antarctic, because you've got a giant ice sheet, obviously, or two ice sheets down in the Antarctic as well. But it's changing the jet stream that actually affects the precipitation patterns as well as the temperature going up. So rain and snow are shown, changes are shown on the lower two maps. I should say that this is a low, the left-hand maps are for what we call a low emissions pathway, which is, we're not following anywhere near at the moment. What we're following so far is more like this one, these maps on the right, which are high emissions pathway. You can see that even with the low emissions pathway, you've still got quite significant climate changes. But here, we're talking about something like 50% increase or decrease in precipitation, depending on what parts of the world you're in. So here it's going down, in other parts it's going up. But basically, it's obviously we're already seeing some of those changes from the observed record. If anyone wants to read in more detail, I've got a paper there. There's a summary, and 2 minutes and it will be lunchtime. So we have time for a couple of quick questions. But otherwise, I'm happy to talk to people over lunch. So I'll take a couple of quick questions now. Sorry, I'll put the light back up. Yes,
yeah,
sorry.
I have two questions. One about the weighting on the jet stream.
Yes. Yes, I'll just go.
If I look at that graph, I actually see the opposite happening in the Pacific, in the North Pacific, as was happening in the North Atlantic. So it looks.
So there's this region here. So
right. So
yes.
it looks to me like it's gotten less weighty in the North Pacific than it was before.
Yes, I mean the issue. One of the issues I raised, which is it's a very good observation you make, Professor Holland, is with the natural variability and the relatively short record, but also different mechanisms happening regionally in different parts of the world, and we don't fully understand all of these because actually we have models as well that drive the jet stream. I work with engineers. We construct models that actually a number of factors, as you well know, go into driving the jet stream. Yes, regionally it does vary. So as I said, it's near the top of the slide where we've got the increased waviness. But of course, that North Atlantic sector is critical for much of Eurasia, North America. So the land-based populations where you've got hundreds of millions of people living directly in those mid-latitude zones. So I've not seen actually many studies that have looked at this directly over the Pacific at the regional level rather than just say at the global level. So I think there needs to be more work, but also it's a relatively short time period. But the effects over the North Atlantic are fairly clear.
So if it were me redoing that analysis focused on the Pacific, I would use the Pacific decadal oscillation as the cutoff, because the PDO
Yes.
is actually a quite a long
Yes.
time scale oscillation. And I know I think it flipped in around 2015.
Yes, yes. So I work with, do you know James Overland at NOAA and Jennifer Francis, who published quite a lot on
I
jet
know
stream.
colleagues that Jennifer has worked with at Cornell.
Yeah, so some of them have looked more specifically at the Pacific and the PDO, but the North Atlantic and European climate is more affected by the North Atlantic oscillation, of course, which is why I focus more on my studies mainly on this region.
Yeah, justifiably, but I always see things through Pacific lens now.
Well, we've got to look at all these areas, and these ideas are quite new, so of course they've not been fully researched yet.
So if you wouldn't mind just going to the precip graph?
Absolutely.
The question I have there, and this is my own naivete, is can you tell me why is it that you have as much shift in precipitation for the tropics in the right-hand bottom panel as you have for the Arctic?
This is the IPC. This is the AR5.
Yeah, the IPCC one. So you see the precipitation band around the tropics
Yes.
over the Pacific?
Yes.
That shift in precipitation is of almost the same magnitude as the Arctic shift in precipitation. What's going on there?
I think, is it not the warming of the tropical sea surface temperatures that increase convection over the Pacific Ocean, plus probably an increased frequency and intensity of the stronger El Nino episodes? Obviously there's different types of El Nino events, but some models seem to suggest that those increase, and so that would warm, particularly the Western Pacific further. So yes, but this is a synthesis of the available climate models that were published in the report that you were more directly involved in than myself. So this is an agreed IPCC output, isn't it?
And none of them are particularly robust on modeling El Nino.
Or for the North Atlantic, for that matter. So I've done a bit of work for Greenland in the North Atlantic. The latest generation of the sixth generation of climate models, the CMIP6, are not necessarily much better than the fifth generation, unfortunately, at the regional level. So, but I think, look, yes, in tropical Pacific, I'm not obviously a tropical Pacific specialist at all, but the general feeling is the precip goes up there from studies that I've read, I think. Anyway, we're out of time, I think. I don't want to keep anyone from lunch, but yes, so we've got lunch now, and do feel free to talk to me over lunch if you wish. Otherwise, we'll be back in the other, the previous room, the Jackson. I'll just give you the time. 1:30.